Have you ever tried to listen for a whisper in a crowded room? It's incredibly difficult. Your brain has to work hard to filter out all the background noise to focus on that one tiny sound. In the world of electronics, a differential operational amplifier, or op-amp, does something very similar. It's a tiny electronic detective designed to listen for a very specific type of signal. The difference in electrical pressure, or voltage, between 2 points. It has two inputs, one called the inverting and one called the non-inverting, and its entire job is to pay incredibly close attention to the voltage on each one. Inside this tiny silicon chip is a marvel of engineering. The first stage, known as the differential pair, consists of two transistors that are intricately linked together. Think of them as two sides of a perfectly balanced scale. When the voltage on both input pins is exactly the same, the scale is level, and the transistors share the electrical current flowing through them equally. But the moment one input's voltage becomes even slightly higher or lower than the other, the scale tips. More current flows through one transistor than the other. This imbalance is the first crucial step in detecting the signal. This internal tug-of-war over electrical current is the secret to the op-amp's sensitivity. Even a minuscule difference in voltage, something as small as a few millionths of a volt, can cause a noticeable shift in how the current is distributed between those two initial transistors. The rest of the circuitry inside the op-amp is designed to take this tiny, lopsided current flow and amplify it, making it much, much bigger. It's like taking that faint whisper and running it through a massive megaphone, turning it into a signal that is strong, clear, and easy for other electronic components to measure and understand. The final output of the op-amp is a direct consequence of this internal amplification. If the non-inverting input has a higher voltage, the output voltage swings high. If the inverting input has the higher voltage, the output swings low. The size of that output swing is proportional to the difference between the inputs, but it's magnified by an enormous factor, often hundreds of thousands of times. This raw power is what makes the op-amp so useful, but as we'll see, it's a power that needs to be carefully tamed with a clever trick called negative feedback to do any useful work. Imagine trying to perfectly balance a seesaw with two people of different weights. It's nearly impossible without some help. You might add or subtract weight from one side to get it level. An op-amp in a differential configuration uses a similar balancing act through a concept called negative feedback. This is where we connect the output of the op-amp back to its own inverting input through a resistor. This connection creates a self-correcting loop. The op-amp is always trying to adjust its own output in a way that makes the voltage difference between its two input pins zero. This relentless drive to zero out the input difference creates a fascinating phenomenon known as the virtual short or virtual ground. The two input pins, the inverting and non-inverting, are not actually physically connected inside the chip. But because of the negative feedback loop, the op-amp works so tirelessly to keep their voltages equal that they behave as if they were shorted together. It's a delicate, electronically enforced truce. If the voltage at the inverting input starts to drift away from the non-inverting input's voltage, the output immediately changes to nudge it right back into place. Let's trace the flow of electricity to understand this better. A signal comes into the circuit, causing a slight voltage imbalance at the inputs. The op-amp's internal machinery instantly detects this and sends a powerful, amplified signal out of its output pin. Because of our feedback resistor, a portion of this output signal is sent directly back to the inverting input. This feedback current pushes against the original change, effectively cancelling it out at the input pin. It's like a thermostat in your house. If the room gets too hot, the system turns on the air conditioning to bring the temperature back down to the set point. This continuous process of monitoring and correcting is what makes the differential amplifier stable and predictable. Without negative feedback, the op-amp's massive amplification would make it wildly unstable. The tiniest bit of input noise would send the output swinging uncontrollably to its maximum or minimum voltage. But with feedback, we tame the beast. The circuit settles into a calm, balanced state, where the output is a precise and controlled amplification of the difference between the signals we are truly interested in, all thanks to the elegant illusion of the virtual short. Now let's go back to our analogy of listening for a whisper in a crowd. The whisper is our desired signal. The chatter of the crowd is common mode noise, unwanted electrical interference that is present on both of our input lines at the same time. This could be 60 Hz hum from power lines, radio frequency interference from a nearby cell phone, or electrical noise from motors in a factory. A key strength of the differential amplifier is its amazing ability to ignore this common noise, a property we call common mode rejection ratio, or CMRR. The circuit accomplishes this feat because it's fundamentally designed to only amplify the difference between its inputs. Imagine two people whispering the exact same message into both of your ears simultaneously. You wouldn't perceive a difference. Similarly, if the same noise voltage appears on both the inverting and non-inverting inputs, the op-amp sees no difference between them. Since there's no difference, there's nothing to amplify. The common mode noise is effectively invisible to the amplifier, and the output remains unaffected. It's a simple yet profoundly powerful principle. However, this magic trick depends on one critical condition: perfect balance. The network of resistors used to build the differential amplifier circuit must be exquisitely matched. Think of it like a perfectly balanced pair of scales again. If the resistors on the inverting side are not precisely equal to the resistors on the non-inverting side, the scales are tipped from the start. A common mode signal, which should be ignored, will now create a small but real voltage difference at the op-amp's inputs because of this resistor mismatch. The op-amp, doing its job, will then amplify this unwanted signal right along with our real one. This is why engineers go to great lengths to use high-precision, matched resistors when building differential amplifiers. A 1% difference in resistor values might seem small, but it can significantly degrade the amplifier's ability to reject common mode noise. In sensitive applications, even tiny mismatches can allow unwanted noise to creep in and corrupt the measurement. Achieving high common mode rejection isn't just about the op-amp itself. It's about the careful, symmetrical design of the entire circuit around it, ensuring that the only thing the amplifier hears is the true signal we want to measure. The principles we've explored aren't just textbook theory. They are the foundation of countless technologies that shape our modern world. One of the most incredible applications is in biomedical engineering. When a doctor performs an electrocardiogram to measure the electrical activity of your heart, the signals are incredibly faint, just a few thousandths of a volt. On top of that, the human body acts like a giant antenna, picking up all sorts of electrical noise from the room. A differential amplifier is perfect for this. It can be connected to two electrodes on the body, amplifying the tiny voltage difference created by the heartbeat, while rejecting the much larger common mode noise that both electrodes pick up. This same principle is essential in industrial settings. Imagine a factory filled with heavy machinery, motors, and high-voltage power lines. Trying to measure a precise temperature or pressure signal from a sensor in this environment is a nightmare. The sensor's weak signal can be easily swamped by the massive electrical noise. By using a differential amplifier, engineers can run two wires from the sensor to the measurement device. The amplifier looks only at the difference between the two wires, the true sensor signal, and ignores the noise that contaminates both wires equally. This allows for reliable and accurate control systems even in the harshest electrical environments. Another critical field is data acquisition the backbone of scientific research and testing. When scientists or engineers need to make ultra-precise measurements, whether it's the output of a delicate scientific instrument or the performance of a new prototype, accuracy is everything. Differential amplifiers are used to create instrumentation amplifiers, which are specialized circuits that provide extremely high input impedance and superior common mode rejection. This ensures that the measurement device doesn't interfere with the circuit being tested, and that the data collected is a pure, uncorrupted representation of the physical phenomenon. From measuring the faint electrical whispers of the brain to ensuring the audio in a professional recording studio is free from hum, the differential amplifier is a trusted and indispensable tool. Its elegant ability to distinguish a meaningful signal from a sea of noise is a testament to clever engineering. It works by creating a stable, balanced system that focuses only on what's different, allowing us to see and measure the world with a clarity that would otherwise be impossible. It's a simple concept with a powerful impact, quietly working behind the scenes in the technology we rely on every single day.